and discussions on this topic today. Now, before we get started, there are a couple of logistics things that I would like to point out to you. One of the things is everybody's on mute in this webinar except myself. And for you to be able to ask any questions, we've provided on the control panel on the right-hand side the ability to chat. There are a couple of people standing by that will be answering all the questions that you'd be asking, and they can immediately respond to all of your questions. So feel free to type in any of your questions while the presentation is ongoing. At the end of the session, we will provide some time for asking questions as well. So feel free to either ask during the session or at the end of the session also you can ask questions. There are a lot of people standing by to help you out. For those of you that have just joined us, good morning and or good afternoon. Welcome to the Mirrorless Designs webinar on model-based certification architecture exploration of avionics systems. Today what I'm going to talk about starts off with the connection between certification and architecture exploration, then talk a little bit about the systems engineering process that makes this possible, and then come up with a discussion on all the different things associated with electronics in aerospace, primarily the migration from a distributed architecture to an integrated modular architecture, looking at the metrics around performance, power, and functionality, and finally using a model-based systems engineering tool to allow you to define the system, create tests, and do analysis. The session is going to be for about 45 minutes, followed by a little bit of time provided for questions and answers. One of the key things in certification and testing is to fully understand where your system is going to cause problems or where your systems are going to have bottlenecks. Some of the areas of bottlenecks can be buffering, can be related to latency, can be related to power consumption, can be related to traces, can be any of those. In this particular example that I'm showing you here, we're going to take a simple example of a single circuit board with two processors, a DSP and an I/O interface connected through two buses and a bridge in the middle. We're going to consider some use cases on this particular system and then look at the latency and power consumption that is generated as a result of that. So when you have a single sub use case, it's fairly easy to describe what the behavior is going to be. It's also easy to be able to predict the scheduling, the arbitration, and the power consumption. Now, when you expand the system to multiple applications, then the question of resources start playing a role. There's going to be shared resources, there's going to be buffering, there's going to be a lot more arbitrations. All of these lead to a number of anomalies that you would start making predictions if you used analytical methods that can be significantly inaccurate. The contention being one of the main reasons. For example, in this particular system, when we ran the simulation, we tried out two experiments. One was a 200 megahertz system. The other one was a 400 megahertz system. And one of the things we discovered was the unpredictable system response, where if you notice these circles right in these positions here, you will see that these positions here have a latency that's significantly higher. So for example, the red dots here signify 200 megahertz, the blue dots signify 400 megahertz bus structure. You'll notice that at many points in the simulation time period, the 400 megahertz simulation actually generates a much greater, in some cases about 40–50% greater end-to-end response time or latency. As a result of which, you could actually have a testing failure even though you oversubscribe the system. Now, a quick introduction to Mirabilis Design before I proceed. We're a software company based in Sunnyvale, California, providing software tools for aerospace and space system exploration and certification testing. Our environment allows you to define systems, semiconductors, embedded software, hydromechanical, and other kinds of electrical systems, put it all together and be able to figure out the right configuration to meet your customer requirements. The product is called VisualSim Architect, and VisualSim Architect allows you to create these models where you can evaluate the power, performance, and functionality in a completely graphical environment. Look at ways how you can minimize cost and primarily avoid surprises in the implementation or in the post-deployment process. And the purpose of doing that is to really get the maximum out of your system, both from a use case functionality standpoint, but also from a reliability throughput standpoint as well. Now, look back at the systems engineering process and why a system design tool, especially with a simulation approach, can really bring about a dramatic change in your certification process. Now, before we do that, I'm just going to walk you through a simple example to show you what we're discussing. And to do that, I'm actually going to bring up a system that we just discussed a few minutes ago, which was this circuit board with like 2 processors, buses, bridges, IOs, and DSP. In this case, what you're going to notice is we've got 2 different use cases running through this particular system. Now I'm going to go ahead and click on this go button here, and what's going to happen is a variety of plots or analysis are going to be showing up. The first one that you can see over here is a power plot, and as I zoom into some regions over here, what you can see is a peak power consumption in watts versus an average power consumption which is fairly flat. Now, what we're also going to see is a histogram where we're looking at the latencies, which if you look at these yellow bins over here, that corresponds to the total time taken combining the communication and the processing latency. The 2 most important things when you're looking at certification for the timing or meeting the deadlines. Now, these yellow lines correspond to a combination of these red lines, which are the processing, and these deep blue lines over here, which are the communication, which is all the transfer of data across either a network or across serial switches or buses or any other structures. Now, that is for application 1. Now, the second use case, you can see that it has a much longer tail for the actual latency. So it actually extends from about 1.1 microsecond to about 1.65 microseconds, almost a 50% difference. And the reason you can see is that the processing time over, or the processing latency over time is actually quite significant duration, 0.65 to about 1.2, over 50%. While the, in some cases, when I look at this region here, the communication latency is actually fairly close to the actual processing latency. The addition of the communication latency or being able to predict your communication latency is an important aspect of making sure that you can meet your timing deadlines. Now, these are some of the tests that you can deploy in your system to be able to compute what your expected latencies, what your expected deadline should be, either for power or for performance, before you actually start doing the deployment or before you actually start doing implementation, so you can incorporate it into your final certification and test as well. As I mentioned earlier, there is this ability for you to be able to ask any questions through the chat window in the control panel as well. Now, going back to the systems engineering process, as you saw there, that was a single circuit board. Now, You can obviously expand this to include your power systems, your hardware, your software, your thermal, your mechanical, all of the subsystems, and then apply a variety of tests. Now, all of these are done at the systems engineering, which means the information that is delivered from here can be fed down to your domain level tools, which are the native tools that you would use for a variety of things like your heat dissipation analysis or your mechanical structure, your civil structure, or your hydro components as well. So if you take the example of a UAV or a spacecraft, the left-hand side over here is the use case, which in this case has a start, going through all the steps, and to a stop state. The right-hand side over here includes all of the system components. In this system over here, we're only focusing on a few of the elements, which is the hardware, software, power systems, the RF or the data link, the GPS, and the thermal. Now, as you can see, the domain level design tools are right at the bottom. The mechanical structure is fixed, and the information is shared between the domain tools and the system model right over here. Now, the whole idea here is to be able to simulate this test case over the system model to be able to predict the different aspects, either in terms of metrics or the available bandwidth or any sort of deadlines. I'm going to move from here to a representation of this particular system in a graphical environment. As you can see here, we have the entire system right from the avionics to the engine, propulsion, the RF data link, GPS alternator, the thermal system, the payload, and the power system. Now, what I have over here is the table of the use cases, which are all the different states over here with the associated power and for the actual power in the different subsystems. While it's actually in each of these different states. Now, what we're going to do is I'm going to go ahead and run the simulation to be able to look at a few of the very specific plots of interest for us. One of them is looking at what the link margin is, which provides you over the simulation time. As you can see over here in the latency plot, the latency actually changes over time, which is related to which state the UAV is at any state in time. And this one here corresponds to the available link margin for the UAV being in those different states. Now, right over here shows you what is the power consumption over time for this particular design as well. And it shows you the, for what is its current state and what's the power consumption in those different states. So you can actually combine your latency, your link margins, your power consumption, and possibly even your traces or your flow control to be able to evaluate what is your system operation. Now, looking at some of the things of electronics in aerospace, there are really three types. There's the avionics, which is the massive data movement, requires large communication bandwidth and high performance processing systems. The second one is how to control the electrical and mechanical substance, which doesn't require a lot of processing, it's low bandwidth, but then very deterministic and real-time responses. The last one is looking at more focused processing with very symmetrical and predictable data patterns of things like communication, multimedia, storage, navigation, and such components that require more triggers than and maybe some very specific data patterns to specific instrument panels and things like that, or to display panels. Now, when I look at architecture exploration, how it impacts the overall testing process, a number of things can have to be done at the systems engineering phase to be able to say that your certification is going to be successful or provide sufficient input for your certification. The first and foremost is feasibility. There's both project level feasibility, is this going to be able to work, meaning is my size, weight, heat dissipation, and other aspects like cost and resource requirements going to be met. Second one is, what is the sizing? How fast should my system be? How much of memory do I need? How much of bandwidth do I require? How much of power do I require to be able to meet my requirements from the first phase there? Third one is really about the certification, which is how does my system behave in various use cases? Like you just saw use case of a UAV, there can be other types of use cases. For example, in a spacecraft, you might be looking at the orbit and seeing what happens when I'm in telemetry state or in command and control or like image capture or image processing or a setup phase. So how does it go? What is the timing? What's the power? What's the trace? All of those attributes related for certification. The next is the power consumption. Many of our systems are running on batteries or motors which do have limited amount of power. So looking at aspects where we can either both measure what the power consumption is going to be for the certification to make sure you're actually not exceeding the power, but also looking at ways to manage the power. How can I reduce the power consumption? The other thing, and probably the most important aspect, which is really about the software side, which is about meeting the deadline, which is things like, are we scheduling the sequence of tasks? What is the ordering? What is the resource allocation? Resources can be soft resources like semaphores, can also be hard resources like a particular device or a particular electromechanical system. The other aspect of certification is really the latency, and there's two parts to it. We talked about the hardware sizing, which is the processing latency, and this one is about the network topology, which is more of the communication latency. Finally, the last one, which is about reliability, which is really injecting faults into the system and looking at error conditions, how does a redundant path operating, is it still meeting all the requirements of my system as a result of all the reliability aspects. Now, when you look at the complex tests that have to be designed for the certification and for the architecture exploration, some of the things we already talked about are the end-to-end latency, communication versus processing, the flow trace, which is really all the sensors data arriving and are they being fed to the correct attenuators, looking at the schedule and making sure that all the tasks are arriving within the deadline, so that way the future tasks are also being completed within the deadline, not flowing over. Then looking at the power consumption, especially the peak power consumption, which also relates to battery charging and discharging both in an eclipse and when you're using a solar panel or the motor is working at full capacity. At this point, I'm going to go over and show you a very active architecture today, which is based on an AFDX based network. So what you have over here is a redundant switch architecture made up of about 30 or 40 different devices that are connected together through the this AFDX switch network. Has anything from low rate transmitter receivers at 10 megahertz to CCTVs to IP phones and a variety of other interfaces. What we have here is when I double click on any one of these, you can see it has a variety of parameters that can be modified to be able to evaluate the behavior of a system for a variety of situations. These are very specific to the AFDX, which is the VLAN. But then there are other things like, for example, the routing table, which is the connectivity, the distances between the switch and the device, the clock speeds of the different networks. So you can actually set up the hardware, the software, the communication network, and also the workloads associated with the individual systems here as well, which is also related to the traffic table right over here. So it tells me what the megabytes, what's the size, what period of time it's going to be running, what kind of a protocol, what is the type, what's the priority, all of that type of information as well can be modified and be able to run a variety of iterations of the simulation. And when I go ahead and again click on the Go button to run a simulation, what you're going to be able to see is a different type or a different set of results that are really focused on the ability for the switch architecture here in the backbone to be able to meet the timing deadlines that are required by this particular architecture. So for example, if I'm going to be communicating between the transmitter receiver over here at 100 megahertz to say the IP phone or the CCTV, what is going to be the response time, and also how much of bandwidth out of that VLAN is really being consumed by that particular device. So for example, the thing we're going to look at here is what is the overall latency for each of these different interfaces or devices over the period of the simulation. So as you can see over here, most of these are running in millisecond ranges. So if I zoom into a region, each of these colors signify one of the different devices that we have here. And as I extend it, you can actually see the latency for each of the devices. At the same time, you can see a textual description of what the end-to-end latency computed for each of the devices as well. In addition to that, what we also see is what is a network latency. One is a communication latency, which is this one over here, and then the other one is a processing latency. In this case, we are looking at the overall network, so we're only focusing on what is a network latency across all these subsystems right over here. So again, we looked at a variety of things: power, latency, traces, and what we're also going to look at now is look at an example of an integrated modular architecture for avionics, which the previous one was a precursor to this, which was using the AFDX, but now we're going to use one which has got a variety of different protocols that are being incorporated into this particular system. So when I look at this particular design, we're using a VPX backbone that connects all the processors, the graphic cards, the IOs, and a vast number of interfaces to this particular system. Now what we have is we have two power cards in the system. One of the things we're going to do as part of this architecture is look at whether the system is still able to continue to behave when one of the power cords is accidentally dropped, which means it's no longer operational. So we're actually going to look at the what the latency, behavior, and power consumption is going to be. We're looking at the trade-off between all of them. So we're going to go back into the demo to look at the latency trade-off here. So as you can see, there's a number of slots which is related to the ARINC the RTOS, the ARINC RTOS, and there's actually the tasks that are being assigned to these different slots on the processor card. What we're going to look at now is we're going to go ahead and run the simulation. You can actually see what the activity trace is on these different slots. So slot 2, for example, is from 20 to 60, while slot 3 is from, slot 2 is from 20 to 40, slot 3 is from 40 to 60. Similarly, here's a very important aspect that again becomes part of your testing and certification, which is over the time, how many of these tasks were not being able to complete as a result of the unavailability of either unavailability of resources or unavailability of slot time remaining. So you can see over time, so actually one of the things you notice is slot 3 has a huge number of tasks that actually failed and didn't complete. Now you can actually see that this is the cord that was disconnected, the power cord that was disconnected, and you can see what the load was on the other power cord. So you can actually predict. In this case, it's about 4 times 10 to the power 2, so it's about 400 watts of power is required off a single power cord. So now you can actually see, will my system be able to handle if one of the power cords fails? Again, part of your testing process to validate that this architecture is going to meet your certification needs. Now, one of the aspects that we also always look at is a trade-off between spreadsheets or analytical methods and simulation. So in this particular system, what we did was, when we ran the system, we did an analytical analysis of actually computing what is the total power consumption for this particular architecture by taking down the power consumed by each of the individual components on the circuit board. Now, one of the things you'll notice is this value here matches this active time right over here. But then when you start applying the different use cases, the power becomes variable. And this is where there's a divergence for simulation-based modeling over analytical methods. And that's where your network-based calculus or other types of prediction, like worst-case execution time analysis, spreadsheet-based power analysis, can actually fail when you present it for certification. And this is where tools like VisualSim and other model-based system analysis tools allow you to be able to very accurately predict with a high level of probability what that consumption is going to be. Now, one of the other aspects for certification that we actually evaluate is in terms of fault injection. So all these systems work fine in a normal condition, which is, I can size my hardware system, I can make sure my DMAs are correct, my buffering is correct, so when the mechanical or MEMS device requires data, it's always available. Now, what happens in these perfectly working systems, something fails. Some of the failures can be more slow in terms of, the number of coils that are loosening out, which means the power generated starts reducing. Doesn't drop to zero, starts reducing. At some point, you get an overload, which means that some of the critical devices have to be shut down. What is that particular point? So be able to know that. The other aspect is looking at the redundant systems and seeing whether if one of the systems really fails, will those other systems be able to handle the load, like we looked at the power cord measurement. The other one is looking at software failures. What happens if the schedule table gets modified or the memory value changes? Can it still meet the deadline? So now we're actually going to look at an analysis. So this is a system where we're looking at a scheduling-based operating system which has a large number of tasks that are running concurrently through the system. Now, what we have here is a schedule table that has these event triggers that trigger the different tasks. So those are the different task points and the timing offset for those. Now, there is the actual task itself, which shows me a list of software code that runs and what is the sequence and what is the priority and information such as that. And lastly, there's the priority of the different tasks. Now, what I'm going to do is going to go ahead and run the simulation, and I'm only going to focus on one aspect, which is really the deadline. So what I'm going to do is actually zoom into this particular region, and I'm going to focus on just a few tasks here, which is right over here. So what we're going to notice is you see that this is the T2 or the trigger for task 2. But notice that the actual task does not get executed until this point over here. I'm sorry, until this point over here. The reason being is this task here, which is the prior task, actually got only triggered at this point, and it ended up right over here, which means the next task couldn't start up until this point over here. Now you think that the problem is right over here. In reality, the thing is as a result of this task over here getting delayed is causing a trigger. Sorry, I'm going to actually zoom back into this region here again. It's really about this task here not completing, which is causing this task from the previous flow, which is this flow over here. It's causing this task to move over to the next time period, which is delaying this task, which causes this task to fail. So even though we can say that this task failed as part of our certification, in reality, it's this particular task here, the runnable 3, that has failed, that has caused this task to fail. So one of the things that the simulation can allow you to do is be able to work your way backwards to figure out which task actually failed and what was the cause of the failure. And that can help you predict what your system needs to do or what you need to counter in your design to be able to ensure that this deadline failure does not occur. As I mentioned earlier, there's always opportunities for you to ask questions through the presentation. There's actually a chat window on the right-hand side in your control panel, and there are actual people waiting by to answer any of your questions. Now, one of the things is when you look at the systems engineering cycle, it's very important that you carry everything that you define early in the architecture phase all the way down through whether it's your orbit analysis or your flight path analysis or even the actual deployment phase. The reason is you have a set of tests that are set up right at the beginning of the design process that can be carried through with the accompanying results all the way through your debugging, test and verification, actually the actual deployment. So an example can be is you can actually see what happens from T-minus 30 from liftoff or from flight takeoff to T plus 30 for like the the avionics system or maybe some of your fuel injection systems or things like that, and look at whether the test results that were set up during the architecture phase are going to be valid to the actual deployment phase, which again is part of the measurements that needs to be provided as part of your feedback to the OEM or even as part of the certification process before you can actually deploy it on the real system. So as you can see here, the understanding the requirements is where you can determine what are all the different test scenarios that are going to be required, because as you run the simulation, you will see what are the different faults that are going to be generated, what are the different bottlenecks. So you can have associated tests for each one of those scenarios. Now, the other aspect is really comparing. This is my development, and here's my architecture model. And how do they really compare between the two of them? And finally, you can even provide the input traffic trace from the real system back to the actual system model and be able to compare them and see how the system actually measures. So you have your original architecture, you have the input traffic traces, which are the real system after you enter. It's really the process of communication, which is you have architects that are defining the system, and then you have the users or the end users that would be people that are building tests, the suppliers, your partners, your engineering consulting divisions, or even your OEM or even the final end customer as well. So the process is being able to bridge the gap, and the way to do it is be able to share your models that you're going to be using for defining a certification and things like that with your with the rest of the team or with the rest of the engineers. So here's where you have an integrated modular avionics system that you have all your definition of all the different aspects of it, all your analysis, all the different, so these are your different IOs and the different clock speeds and what the utilizations you get, the latencies, the bandwidth, all of this information you can share with your clients or with the OEM. But at the same time, you can also share the actual models that go with the design. And let me just bring up one of those. So what I've done is I've connected to a website which is located in Houston, Texas, and created a private cloud within my environment from which, so right here from Houston, Texas, my model actually got loaded up. So in your particular case, this is a technology which will be a private cloud within your network that will be made available. Anyone who has access to that web page or with the documentation can actually go in, view the model, look at the parameters, even change some of these parameter values, and then be able to run simulations right from within the browser. There's no need for you to actually provide the actual software or let this outside your organization, none of those things. It's all running within your own private cloud. As a matter of fact, if you remember, this was the same model that was shown a little while ago, and you can actually see how this model is actually running right from here. So the user can actually make changes. For example, they can change this to say 8 slots on my Arinka TOS, and then I can look at how the system behaves when I migrate to more number of slots here, and how does the system operate. So you can do that right from within the browser itself. There's no need for you to actually go in and be able to ship the model off and things like that. These are a large number of the IPs that are provided in our environment, and this collection of IPs is what ensures that you can very quickly model the system, do the testing, and be able to provide feedback on what is the expectation in terms of meeting the requirements and what should be the items that need to be tested more elaborately during your implementation. With this, I would like to conclude our presentation. At this point, I'm going to be opening this session up to everyone. Anyone that has any questions can feel free to ask these questions, and there will be folks standing by to answer them.